welcome to the show today.
It's great to be here. Thanks for inviting me.
You're very welcome. If you don't mind, I'd like to ask you a few questions about your specialty, and then we can get into a little discussion maybe, or just let it go as it is. First off, I said you work at CERN in Switzerland. What is CERN?
CERN is the largest and most prestigious laboratory in the world that does particle physics right now. It's on the border of Switzerland and France, and it's an international laboratory. People work there from all over the world, and the goal of CERN primarily is to understand the basic structure of the universe and the forces that hold the fundamental particles together. And right now, the largest experimental machine at CERN is, as you said, the Large Hadron Collider. It's a tunnel about 17 miles in circumference under the ground. It runs under the Swiss-French border. And inside that tunnel are superconducting magnets that and electronics and electric fields that accelerate protons to nearly the speed of light and then smash protons together. And we look at the debris of that collision, and from seeing what happens when the protons collide, we understand the structure and somewhat the origin of the universe as well.
Sounds a bit like hitting an alarm clock with a hammer and seeing what comes out.
Yeah, the analogy I often give is if you want to know what a car is made of and you don't have any tools to take the car apart and see how it works, and you're an experimental particle physicist, you get two cars going really, really fast, smash them together and see what comes out.
Nice, nice. So with your background, your PhD from UCLA, how did you get interested in quantum mechanics in particular?
So, you know, I was as an undergrad, I was what was called a physical science major, kind of a mixture of physics, chemistry, and math at Biola University in Los Angeles. And the first class I took on quantum mechanics just fascinated me. It was a science that was developed originally in the early 20th century. It revolutionized the way we think about the universe. And it's very much anti-intuitive in some sense, but yet it's very much describes the universe we live in. And there's so many bizarre aspects of it, we'll talk about some of those, that it just fascinated me. And when I got to graduate school, as I began to think about what I wanted to do for a career, it was this subject of quantum mechanics that was so intriguing. And I said, I want to do something that ultimately deals with quantum mechanics.
Excellent, excellent. So we mentioned quantum mechanics a couple of times. How did quantum mechanics get started? And if you don't mind, what does it mean?
Yeah, so we didn't even define what it is. It has to do with how the universe works at all scales, but particularly it's noticeable at very, very small scales. The size of atoms are smaller. The word quantum comes from a word that means something like, I don't know exactly, but discrete. It's like if you wanted to climb a hill and the hill was sloped, that would be like analog. In other words, you could be at any height along the hill, but if you wanted to climb a hill and there were steps, you could not be at any height. You could only be at certain heights, and those heights would be quantized. That is, they would be discrete heights. And so the word quantum mechanics comes from this idea of quantization, that certain things are found only at specific values and not in between those values. And things like energy levels in atoms and other things are actually quantized. And so like steps, they come in discrete levels. It was discovered originally in around the 1920s and later developed further, and quantum mechanics at very high speeds that we call relativistic quantum mechanics was developed later. Quantum field theories, which describe particles, was even developed in the 50s and 60s and beyond that. So it really revolutionized the science in the 20th century.
So who discovered that things work this way?
It's a great question. It was really collaboration of many, many famous people. Niels Bohr is a name that comes up a lot. Aaron Schrodinger is a name that comes up a lot. Heisenberg, which we'll talk about him. Paul Dirac for relativistic quantum mechanics. Really, there was no person who discovered quantum mechanics. It was a development within the scientific community, both the theoretical community and the experimental community, that gradually grew. There was an early quantum theory and a more revised quantum theory, but some of the names I mentioned are those that are often associated with the discoveries.
So we've talked before about this a little bit, and you mentioned that there's a standard model. Could you briefly describe what the standard model is?
Yeah, so quantum mechanics is a big field, but in my specific field, where we try to study the fundamental particles and forces that make up the universe, that is, if you were to boil down the universe to the most basic building blocks, what would they be? The analogy I give is, if you wanted to build a brick house, you see this brick building behind me. The fundamental building blocks of a brick building are the bricks, that's the matter particles. And then what holds the bricks together is the mortar, and that's the force. And if you have the bricks and the mortar and you understand how they work, you can build any building you want. And so the standard model is the model of the fundamental particles and forces that make up the universe, what they are, how they interact. It was developed kind of originally in the 60s, and the last piece of the standard model that was predicted by the theoretical calculations within the model was something predicted by 6 scientists in the early 60s. One of those was a guy named Peter Higgs. And so the last prediction of the standard model is a particle we call the Higgs boson, which was actually discovered in 2012 at CERN on the experiment. One of the 2 experiments that discovered it is the one I work at, called the Atlas experiment. And so this standard model, which is the scientific model for the fundamental building blocks and particles in the universe, is now confirmed. We'll talk about issues with that. But developed in the 60s and finally completely, I say the last piece of the puzzle of the standard model was finally put into place when the Higgs boson was discovered.
Well, you mentioned when you were talking about the bricks and the mortar type thing, you were talking about force carrying particles and matter particles, fermions and bosons. Could you explain that a little bit?
Yeah, so within the science of particle physics, everything that interacts comes in discrete amounts, particles and or quanta. And those particles, some of them are very familiar. Electrons are a fundamental particle. They're one of 6 particles that are called leptons. And this is all part of the mathematics of the standard model. And so they're particles that make up the universe. We know the universe is made of atoms. Atoms have a nuclei at their core, and every nucleus is made of neutrons and protons. And neutrons and protons are not fundamental particles. They're not part of the standard model per se, but they're made of particles called quarks. So the universe is made up of quarks and leptons. Quarks make up neutrons and protons. Electrons are one kind of lepton. And those are the matter particles. They make up the mass of the universe. Well, some of the mass of the universe. We know there's a lot more out there. And then those particles have to be held together somehow. And in quantum mechanics or in quantum field theories, those particles are held together by other particles that are passed back and forth. It's suppose you have 2 basketball players standing apart on a basketball court. And one of the basketball players is a matter particle and the other is another matter particle. And they want to exchange a force between them or information between them. And so one player throws the ball to the other player. And that ball would carry energy and momentum from one player to another. That would be like a force that goes from one player to the other as a particle. And so the forces in the universe that we know of are gravity, electromagnetism, the strong nuclear force, usually just called the strong force, and the weak force. And all of these forces, with the exception of gravity, which we don't know a lot about, have a particle that carries that force. So the matter particles are quarks and leptons. They make up the universe. And the force particles are particles that interact between the matter particles and carry the electromagnetic force or the strong nuclear force from one matter particle to another. I hope that makes sense. It's complicated, but
Sure.
I've tried to simplify it.
I think some people will be interested to know how can you know that? Do you see that, or do you infer that from experiments? How do you kind of know that's what's going on?
So that's a great question. First of all, you can't see with your eyes any of these things. But of course, I can't see heat with my eyes unless I'm wearing thermal goggles, right? And I know that there's heat because I feel it. So there are different kinds of detectors. Your skin detects heat, your eyes detect light. We have detectors that detect the debris of these particles. You have a picture of one behind you. And so these particles, quarks and leptons, are incredibly small. They're so small you can't imagine how small they are. First of all, we don't know how small they are. We only have a limit. But this is their size. So the difference in size between me and a quark, which is a fundamental particle, is the same as the difference in size between me and the distance to the farthest galaxy I can see with my naked eye.
Wow.
So me standing here, a quark is imperceptibly small. But I have a mathematical theory, a model of what should happen when I fire protons together, if they're made of quarks, and if these force particles are what we think. These mathematical models are extremely complicated. So what we do in our experiments is we run the mathematical model, a simulation of what we think should happen if the universe is made up how we think it is, with quarks and leptons and strong nuclear force. And then we run the model, and then we compare what we see in our detector to this very complicated model. And they basically look, I mean, almost exactly, look exactly the same. So we say our model must in some sense describe reality. Now, if you have another model that's totally different, that can give me exactly the same results, your model is just as good. But so far, no one has one. So, you know, we asked, do quarks exist? Well, they are the best explanation for the phenomena that I see in my detectors. If you have a better explanation, yours is better or just as valid or whatever. We talk about them as if they are real. I mean, no one's ever seen an electron. No one's ever seen love. So there are many things that we don't see that we have evidence for. If I was inside my whole life, I live in Oklahoma, so I look outside my office window. I'm not really outside like my picture indicates. I look outside my office window and I see the leaves on the trees moving. Well, if I had never been outside and never experienced wind, I would propose some hypothesis that explains what I see. And if my hypothesis explains everything I see, then you say, well, maybe wind is real. It seems to explain everything I see. And this is how we deal with everything that we see in our detectors, but you don't see the physical objects. Again, it's true of many things in life.
And just to be clear, you're not actually outside, and I'm not actually in the particle detector. Just so we're clear on that.
Right.
I'm actually in my house.
Yes.
So we talked about
my real background in my office is not worth seeing, so this is why we have the fake background. Yes.
And I can tell you that if I showed the real background, my wife would kill me. But we talked about the standard model, and you kind of hinted that there was something not there. Have they found any deviations from the standard model? Have you guys found any?
So this is actually a frustration. So we put the Higgs boson was the last piece of the jigsaw puzzle, the standard model. It's complete. But we all expect there's something else out there. There are things missing in the standard model. When we look at the universe as a whole, we know that from many, many things, the way galaxies rotate, the way light interacts with galaxies, the large-scale structure of the universe, we know that there's, for instance, this thing we've labeled dark matter. It's some kind of matter. It has mass. It interacts by gravity, but we don't know what it is. It's not the stuff we discovered, quarks and leptons. So we know there's things in the universe that are out there that have yet to be discovered. But unfortunately, the standard model works perfectly for everything we have discovered. We've seen no deviations. It's been extremely frustrating. When we turned the Large Hadron Collider on in 2010, we expected to first hopefully discover the Higgs boson, which we did, but second, to see deviations from our expectations. The most exciting things in physics are not always discovering what you already expect, but discovering the things that you didn't expect. And so we all hoped that we would see something that was a complete deviation from our expectation and would point to totally new knowledge in the universe. Unfortunately, that hasn't happened. There have been no deviations from the standard model. Even the hints of deviations have so far proven to be anomalies in our detector and our experiment, not true deviations. So although we know there are things in the universe that we don't know because of dark matter and dark energy and other effects that we see the effects, like you'd see the effect of the wind, but we don't actually see the wind. We can't find what's causing these effects, what deviations should be there. So we're in an exciting place. The standard model is complete, but we're in a frustrating place because we know there's more to it and we can't yet find any evidence beyond the cosmological evidence of what that more actually is.
You know, Mike, I was watching a YouTube video the other day on quantum mechanics, and it was the history of quantum mechanics kind of video with Sean Carroll. And in it, he explained to the audience that he was going to make a decision and send a particle across the world to be into a beam splitter, etc. And that when it came back, it would tell him whether to jump left or right. And when it came back, depending on which way the experiment came out, it came back to him to jump left. And then he explained to the audience that in another universe, he jumped to the right. That he was explaining that in quantum mechanics, there's a many worlds understanding that he ascribes to, that each time a person makes a choice of that sort or that kind of observation of that sort, that the universe branches out. I've also heard of the Copenhagen understanding. Could you briefly explain the differences between the two, and which one do you think has better evidence, or you think is a better explanation?
Yeah, so quantum mechanics is interesting. The mathematics of it is very precise, and in some sense, the predictions it makes are very precise. It has what's called a wave equation that evolves with time, it changes with time, and the wave equation is what we call a superposition of states often. It's in the world we live in, if I have a penny and I lay it on the ground, it's either heads or tails. But in the mathematics of quantum mechanics, it seems that it can simultaneously both be heads and tails. And the only way it ceases to simultaneously be heads and tails is when I make a measurement of it. And when I look at it, of course, a penny can't simultaneously be heads or tails. It's either heads or tails. But how to interpret the mathematics in the real world is what we call interpretations of quantum mechanics. If you do let's say a Wikipedia search, you'll find a longer entry on interpretations of quantum mechanics than you will on quantum mechanics itself. Wow. The point is, we can do the math. I can tell you what will happen in an experiment on a probabilistic manner. I can tell you if I flip the coin certain amount of times, it's going to be 50% heads and 50% tails with some, random scatter. But I can't tell you how you go from the mathematics to the physical reality. And so there are many interpretations. The Copenhagen interpretation says that when you measure the penny, until I measure it, it's either heads or tails, but when I measure it, it's got to be one or the other. And the act of measuring it forces it to be one or the other. The many worlds interpretation says, no, the act of measuring it just chooses what it is in my universe. So in my universe, if I look at the penny and it's heads, but because there were two options, our universe then at that point branches into two different universes. One is where it's heads and one is where it's tails. It literally creates an entire universe just like ours, where the answer was tails instead of heads. Those two universes don't communicate. They now go on their merry way. So what it means is every time there's a quantum mechanical event, which is in atoms all the time, we get multiple universes, many universes. There would be, an uncountable number of universes then, where everyone is different by a branch where a decision was made. And if the decision had more than one possible outcome, every outcome was experienced in some universe. It's interesting. There are more and more physicists who are actually holding to the many worlds interpretation. The Copenhagen interpretation has long been the predominant interpretation, and there's lots of other ones too. These are maybe two of the more prevalent ones. But lately you've seen more and more physicists who actually are beginning to hold this idea that of many worlds, that every time a quantum event occurs, the universe branches into multiple universes that all go on their merry way. It seems absurd from a logical point of view, but you know, the universe or the universes might be absurd. Who knows? I basically hold to more of a traditional view. I don't know if I totally hold to the Copenhagen view, but you know, I don't believe that at every quantum event, every possible outcome occurs and the universe branches out into all those possible outcomes. But there's no evidence one way or the other at this point.
Are you saying that you possibly think that like a hidden factors type understanding?
There are hidden variable things that say that something actually requires one option to happen. That's a possibility. You know, there's even possibilities that consciousness causes these things to collapse, and that God is that consciousness, for instance. And so I've heard that as an option. I'm an experimental physicist. The beauty of quantum mechanics is it tells me what to expect in my experiment. And then I do the experiment, and that's what I get. I'm not a philosopher. These interpretations to me are more philosophy, unless we can come up with a way to test them. And then they become in the realm of science.
So when you say that the many worlds interpretation is becoming more popular, you're understanding their motivation for the increasing popularity is simply a kind of an embrace of kind of a pantheistic or something of that sort worldview?
Yeah, I hate to ascribe motivation to other people.
Sure.
In some sense, the mathematics almost makes as much sense, if not more, with the many worlds interpretation as any other. And I think you could argue that particularly theoretical physicists trust the mathematics so much, which we should. The mathematics predicted the Higgs boson. The mathematics predicted the existence of antiparticles before they were discovered. And the mathematics, in some sense, hints at the many worlds interpretation. And I think it's maybe that straightforward belief in the mathematics, even though it's not the only, this mathematics is more fuzzy, no pun intended, since quantum mechanics is fuzzy. And I don't think you can say this is really the interpretation of the mathematics, but I could see how a theoretical physicist would say, this to me is the most straightforward interpretation of what the mathematics teaches. And along with it, I get every possibility to happen, and you know, other things as well. So anthropic principles we don't like are less of a problem, and things like that.
So when we talk about these events happening, there's a, like when you're looking for a particle or trying to locate the location, there's a certain level of uncertainty there, and the term Heisenberg uncertainty principle comes up. What is the Heisenberg uncertainty principle?
So it's actually very misunderstood. The Heisenberg uncertainty principle doesn't say that everything or every measurement is uncertain. What it says is there are certain quantities that go together, and that the better I know one of those two quantities, the less I know the other one. And so one of those quantities is position and momentum. The better I know where an object is, the less I know its momentum, which has to do with its velocity. And this seems to be more than just what I can know as an experimenter, as a human. It seems to be maybe an inherent property of nature. If I was to personify nature, it's as if nature herself doesn't know where the particle is if they know the momentum better. That the better nature knows the momentum, the less nature knows the position, and things like that. This plays out in what we call in particle physics virtual particles, particles that seem to violate conservation of energy, but they can only do it for such a very short period of time that they fall within this uncertainty principle. In other words, yeah, I violated conservation of energy, but I did it quick enough that nature wasn't able to observe it in some sense. And so it's a really fundamental principle of nature that there's an inherent trade-off between these quantities, that the better I know the energy of a part, well, energy and time are harder to deal with, but momentum and position are easier to describe. The better I know the position, the worse I know the momentum. Now, we don't notice this in the macroscopic world because the uncertainty is so small. In standard mathematical units, it's on, or in standard physical units that we use, it's on the order of 10 to the minus 36. And so until you could measure the energy in joules to the 36th decimal place, you would never see this in some sense. But we see it in small particles because their mass is so small that those deep decimal places tend to matter. That's a very poor explanation, but basically that's kind of it.
Yeah. Why you kind of hinted at it, I think. Well, why does the uncertainty exist? Because of our limitations? Because the things are so small we're looking at? Or
No, it doesn't seem to be our limitations. It seems to be an inherent property in nature.
mm,
So, people say, well, as a scientist, you're supposed to answer the question why in some sense. But there's always a deeper level. Why does the moon rotate around the Earth? Because of gravity. Why does gravity work? Because massive objects warp space and time according to general relativity. Why do they do that? There comes a point where you say, well, this is the level I know because that's it. Why the uncertainty principle? I don't know. It's part of nature. It's built into the space-time fabric of nature, the laws of nature.
I saw an interview with Stephen Hawking years ago where he was being asked about determinism. And he said that he believed that everything, including our brains, are determined, and therefore there is no free will. But he said, but we don't know what's determined, so we might as well act as if it's not. From that sort of perspective, a materialist understanding of the universe, does the uncertainty principle leave room for free will?
Yeah, so, again, this is a philosophical question. So what I will say is that the uncertainty principle and other aspects of quantum mechanics lay open the possibility that the universe is not deterministic. I think that's certainly clear to most physicists. Again, could something on the quantum level that is, quote, indeterministic affect the macroscopic world? Well, maybe somewhere within my brain. But what does it mean to have free will? Does it truly mean you have to have something totally random occur for me to have free will? I mean, if I was to describe what free will means, are you forcing free will to be random? Well, that doesn't sound like will at all. That doesn't sound free at all.
Sure.
To me, I almost take the same idea as Stephen Hawking. It's a pragmatic viewpoint. I know I have choices. I can choose when the person cuts me off on the freeway to flip that person off or not. I literally have that choice. Now, you might argue, no, you don't. That has to do with your upbringing and your environment and your genetics. But it doesn't feel that way to me. I feel like, and I literally make a choice. I can choose to treat my wife with kindness or not. I can choose to do the chores that she asked me to do or not. I mean, in reality, I have choices. Now, whether or not, you want to go down to the level to say, well, no, you don't, I can't live that way, right? There would be no justice system. There would be no courts if there was no ability to choose. Nobody would be responsible for anything. We just don't live that way. So to me, this is more a pragmatic question than it is. I don't think science, certainly not physics, will ever give us the definitive answer one way or another.
I know. Yeah, go ahead. I'm
But
sorry.
are we going to throw out, culpability And you have to if there's no choice.
Well, it's interesting because Thomas Nagel, the philosopher, he's an atheist, but he wrote a book, Mind and Cosmos, basically delineating this as the problem for him. The subtitle of that book is Why the Neo-Darwinian Materialist Understanding of the Evolution of Life is Almost Certainly False, is because his own experience of intentionality and other aspects of the mind that aren't explained in deterministic terms. So you're right, this is a big philosophical issue. I was just looking for a non-philosopher's approach to it, particularly
Well,
a
and
science.
you probably will have other physicists who try to delve in it from a materialistic viewpoint. Again, one of the reasons I'm an experimental physicist rather than a theoretical physicist, because I like to be able to test things. I like to say, what can I control in this experiment? What can't I, and what results can I expect? And what I do know is that all of my experience says I can make choices. I can choose to fudge on my taxes or not. From every experiential point of view, there seems to be real choice.
Mm. So I think I'd like to kind of move us back towards an area where you'll be a little more comfortable.
No more philosophy. Yeah?
Well, I may slip one of those in. I'm not promising anything, but uh, in the area of understanding the subatomic world, light is understood at one point to be a particle. At another point, they redefined it as a wave moving through an ether. And so the modern time is to go from either or to both and. Is it embracing this idea that light can be a particle and a wave at the same time? How is that possible? It can be two things at once.
Yeah, so let's describe what this is. A particle would be like a billiard ball. If I shoot a billiard ball at another billiard ball, they bounce off each other. A wave would be like a wave on the sea. If you've ever seen waves, they can bend around corners as they go through a jetty or something, or by a jetty. And so waves and particles seem to actually do behave very differently. And so when light was first explored in the 17th, 18th, or 18th and 19th century, it looked a lot like a wave. In fact, the experiments that we did could only be described if light was a wave. But then in the 20th century, we did other experiments that light could only be described, that the results of those experiments could only be described if light was a particle. And so I sometimes teach introductory physics even to non-physics majors, and we talk about the experiments that showed light as a wave, and then we talk about the experiments that show light as a particle. And I ask the students, well, what is it? Is it a wave or a particle? And the answer that they give me, because they've heard, is that it's both. And at that point, I correct them and I say, no. Particles are billiard balls. Waves are on the ocean. They move out. They have wave fronts. Light is neither a wave nor a particle. Light is what it is, and we try to describe it. And we are insufficient to describe it because our experience says everything is a wave or a particle and acts like one of those. Light doesn't behave like that. Light behaves like light. At times it looks like what we call a wave. At times it looks like what we call a particle. What is it? It's light. This is what it is. And I love this analogy because as a Christian and in a spiritual life, it's the same thing. We try to describe God and things we don't understand with these words we do understand. And we say, oh, God must be this and he must be this. And then we go, but those are incompatible. How could he be both? And that's because God is who he is. And we in our finiteness try to describe him. So what is light? It's light. It sometimes looks like what we call a wave. It sometimes acts like what we call a particle. And the amazing thing is it will do what I ask it to do in some sense, unlike God at times. But if I set up an experiment that says, light, show me your wave-like properties, it shows me its wave-like properties. If I set up an experiment that says, light, show me your particle-like properties, it shows me its particle-like properties. And what is it? This is light. I didn't invent it. I just describe it.
So I've seen in the documentary What the F Do We Know and some other sources, they imply that humans somehow cause or influence the results of the test. I've seen some people take it so far as to say that we caused the universe to exist. Our consciousness has caused the universe to exist. Do humans influence the test? How could they?
Again, I can't set up an experiment that says, show me your wave properties and your particle properties at the same time. I can set an experiment that says, show me one of these. And that's what it does. Does that mean I influence it? No. It means I explore what light is like. Yes, of course, if I want to say, well, I think light's a particle, so I'm going to force it to be a particle. Yeah, I set an experiment that only particles can interact. Or if I say, I want to make it a wave, so but am I really doing anything? No. I'm setting up an environment in which light has to show me that property because of the environment I set up. And so I'm not, influencing the universe other than saying, I'm finite. I cannot set up an experiment that says, show me both properties simultaneously. And maybe light can't show me both properties simultaneously. Maybe that's its very nature. And so, this whole idea that I'm the master of the universe because I'm able to make light look like a wave or a particle has everything reversed. No, light is what it is. It's got the upper hand. I just happen to be able to set up experiments that show me its diverse nature. Yes.